Let's go ahead and take a walk through the world of tomorrow called Packetized Telephony. Makes me think of a trip I took out to Florida for Disney World's 50th anniversary. I walked into this area, they had Adventureland and Frontierland, and then they had this one section that especially interested me called Tomorrowland. And I walked into that and I thought, phew, what a jip. No IP telephony. Because that's all tomorrow is going to be about, is we're going to see IP telephony integrating into all the data networks. The first thing I want to talk to you about and show you is the different call control models you can choose to go with. Now, in your network, you'll probably integrate both of the call control models, known as centralized and distributed, together in different situations. We'll talk about that. We'll look at the pieces of IP telephony, kind of in the same way we did in the previous nugget when we looked at traditional telephony and we looked at the pieces of a PBX. It's time to look at the new pieces we can fit together. Finally, I want to hit the thoughts to ponder before you make the jump. A lot of people jump into IP telephony, and I have a couple horror stories I want to tell you about that, because there is one major thing that has to be in place before you can ever dream of IP telephony. Finally, we'll take a look at the IP telephony network designs. There's three major models we can look at and design our networks to. Again, depending on your environment, you'll probably use a combination of all three. Well, let's first off look at the ways to design our network using our call control models. There's really two of them, distributed and centralized. And before we even look at those models, I want to answer the question, what is call control? As in, define this for me. Well, it's kind of like the intelligence of your voice network. See, in the old days, we had these widgets called PBXs, and it was all integrated intelligence. You had your line cards, your trunk cards, and your processing engine inside of there that told your digital phones how to run, how to play dial tone, how to do anything. So in this world, our different devices in our IP telephony network can be the call control. In this case, we have a distributed model, and I have three separate routers here connecting a network together. Now you can see that up here I have a router connected to a PBX, maybe that's using a T1 line or a couple analog ports. We have another router down here connected to the PBX, and then right here I have a router in the middle connected to an IP telephony network with a few IP phones. Now in a distributed call model, we're focusing on where the intelligence is. That's why I have this strange little mouse on the screen. For those of you that don't recognize this famous mouse, this is the brain, as in from the Pinky and the Brain. We used to have this animated cartoon where you had Pinky, which was kind of this goofy sidekick, and the Brain. And the whole purpose of this mouse was to take over the world, and he had the intelligence to do it. Well, in this case, we have the brain inside of each one of these devices, because with distributed call control, each device has all the intelligence of the network. What we'll see in just a moment is something known as centralized call control, where the intelligence really resides in a central location. The advantage of distributed call control is that each router is an independent entity. They don't rely on one another or rely on any centralized source for their intelligence. So if this router down here goes down, oh, let me grab my right tool here. If the router on the bottom goes down, the other routers have no problem. They just know that, mate, we can't seem to reach that PBX, and that's okay. We'll keep working as if nothing happened. That's because all the intelligence is in each one of these. And I emphasize that point because that's going to play a major role when we look at the centralized model and survivability strategies. See, in the centralized call model, we have all the intelligence in a single location. Now in this case, I have this symbol right here that represents a call manager. But it doesn't have to be a call manager. It could be anything. We'll look at some other possibilities of what that could be in a little bit. You can see that the brain right here all resides inside of this call manager. The routers have a little blue link here, and that's not a physical connection or even a way that they're reaching that. That is just kind of a symbolic link, as in they're getting all their intelligence from this centralized source. This works really well if you have a large organization or even a service provider managed environment where they have all the intelligence in their servers, or you have all the intelligence at maybe your corporate headquarters, and all the routers all around the network pull from that. See, this router up here, it's connected to a PBX, but it doesn't know it's connected to a PBX. What happens is when this line goes active, the router begins to panic. It goes, what do I do? I guess this is kind of like Pinky and the Brain. Pinky is kind of the no-name sidekick, and we have the Brain over here. This is Pinky. It's going, what do I do? Brain, tell me. The Brain comes back and says, play dial tone. And the router goes, and that's where it links up to the PBX and plays some dial tone for maybe some phone that could be attached to that PBX sitting right up here. Now, the problem with the centralized call model is you may be zeroing in. Well, first off, before I even say that, the advantage of the centralized model is that you can do all your configuration in one place. You don't have to do repetitive and sometimes error-prone configuration on each and every device in the network. What's more is these devices in a centralized model don't really need to have much memory, much flash, much processing power because they don't really do anything. They just rely on this central source to tell them everything. Now, as you can imagine, the disadvantage is what if the brain dies? What if this centralized call agent goes down? Well, there is ways to make this redundant. I could have redundant call manager servers or redundant H323 gatekeepers, which is another possibility for the centralized intelligent. But what if they go down with it? Well, in that case, all the routers or all the devices, it could be even these IP phones relying on this central source of intelligence. All those devices go dead until at least one of those centralized sources come back online. There will be no calls happening inside of your network. Everything has died. And because of that, a lot of times you'll see people combine the two strategies, in the sense that they'll have a centrally managed source, but they'll have a very small backup configuration on each device. Some people call that SRST, Survivable Remote Site Telephony, which means if the central call source can't be reached or it's down, at that point it kicks over to a secondary configuration, which isn't as heavy as the distributed call processing mode, but it does let your routers keep ticking if the central source is down. Now that we've seen a few of the models, let's start defining the pieces that we've seen in those models and what they're responsible for. This is known as the pieces of IP telephony. As I mentioned at the very beginning, very similar to where we looked at the pieces in a PBX. However, one big difference that you'll see, instead of everything being in one big box, line cards, trunk cards, central processing unit, and switching, everything in a voice over IP network is distributed. And depending on who you talk to, you'll get two different spins on the story. If you talk to a PBX person, they'll go, well, what are you thinking? You have everything spread all out. That's more chance for failure. You lose a switch, you lose a group of phones. You lose a router, you lose your trunk. Everything is kind of a single point of failure in that network. And to the PBX person that says that, I say, I agree. That's true. It is distributed. There is more chance of failure. But let's take the Cisco spin. If you take the Cisco spin on the story, they say, well, that gives you more opportunity to back it up. In this sense, I know this is spinning it in the Cisco direction, but here's the story. A PBX is, as it's defined, a single point of failure. If that one box fails, or inside of that box you lose a power supply and it goes down, that whole network, the whole voice network, is down with it. So in this case, we can actually have redundant voice gateways, redundant switches, redundant routers that allow us to connect through the network. Now, I have to admit, I will be completely honest with you here, I agree more with the PBX person spin. And the only reason why is because I know the uptime of PBXs. They may be a single box, but that is a really reliable box. So, in that sense, IP telephony is still coming along with competing with the 99.999% uptime of a PBX. However, it's almost there. Okay, enough on that. Let's talk about the pieces of IP telephony. Inside of here, the first thing that you see is IP phones. These are going to be phones that are replacing the traditional digital and analog handsets that we see all over the world today. Now, they're not just a phone, and I can't even begin to explain to you how cool these phones are. I've set them up for many companies, and I just, as of 2 weeks ago, set up IP telephony, drum roll please, brrr, psh, in my house where I have IP phones in all of the rooms. The IP phones in the back, when you flip them around, have built-in switch ports, so you can now have a single switch cable. Oh, let me grab the right tool here. Single switch cable going into the phone and then daisy chain your PC from it. Now, if that was all they did, whiz bang wow, it's not that great. These phones right on the screen, just about all Cisco IP phones have the ability to process XML tags, which means you can run just about any XML service on that phone. Check stock quotes, check flight schedules, check news headlines, all essential business need things. Or maybe integrating a time clock. I'll talk more about some of the services that we have later on. And I guess the biggest beauty of all of this is it's running all on top of the data network. Meaning, as a network guy or gal, you have complete control over how that traffic is treated. Priority, you get to combine it with the rest of your traffic. You don't have to buy separate voice lines. It's great. So these IP phones are one of the core new pieces, obviously, of IP telephony. Now over here you see a call agent. The only reason I call it a call agent is because that's what Cisco calls it. Officially, 99% of the time, anytime you see that symbol, it is called the call manager, which is Cisco's product that allows it to be the intelligence of the network. Yes, as of right now, it does run on Windows 2000. It's not as stable as a PBX system, but you can create a cluster of these call manager systems to have a very stable network. These provide the intelligence of your network. Now, with that in mind, one more thought on the call agent, and that is, oh, why it's called a call agent. Sorry, my mind blanked out for a moment. It's called a call agent because this was originally defined by Cisco as an industry standard. See, Cisco created this protocol, and it is called MGCP. You've probably heard about it before, the Media Gateway Control Protocol. Now, when they wrote this protocol, they wanted it to be an industry standard, so they applied for the standards basis and had an RFC created for it and everything like that. It's open source to where anybody can use this protocol. And what this protocol differs from every other protocol out there because it is the only server-client protocol in existence. As of right now, SIP and H323 are all considered peer-to-peer protocols. I'll explain all the differences between them a little bit later. But MGCP is an industry standard protocol, meaning anybody can create their own call agent. Now, the call agent is defined as being the brain of MGCP. All the devices, whether they're phones or gateways or gatekeeper style devices, they'll all look to that call agent for their intelligence. Now, with that in mind, Call Manager is Cisco's implementation of a call agent. So when you're saying call manager, you're talking about a Cisco specific implementation of a call agent. Any company can make their own call agent, and I know the open source community already has. They're all about free stuff, and they've created their own MGCP call agents that you can use, and they each have their own unique names. But by the standard, they're called call agents. I know it's a little bit of semantics, but that's the difference between these two words. Now down here we see the voice gateway and the H323 gatekeeper. You might be looking at those and thinking, well, aren't those the same symbol? Well, yes it is, because typically the gateway and the gatekeeper run on the same type of device, a Cisco voice capable router. Now you notice that this is a router icon with a little V sitting in front of it. Anytime you see that symbol, it just means it's a router that's been upgraded to support voice over IP characteristics. Now, a lot of times that requires more flash, more memory, more processor capabilities. Matter of fact, you may have heard of the 2600, hopefully you have, the 2600 series of routers. Well, Cisco upgraded all those with the 2600 XM series. And the only difference between the 2600 and 2600 XM is how much processor and memory those are capable of using. The voice iOSs that are out there require a much more advanced router that's capable of running all of these features all at the same time. So that's why a lot of times you'll see these voice gateways with a V. It just means increased processor. Now let's focus on the voice gateway itself. The biggest question I think I get in CCNA class when we first get started is students ask me, what's the difference between a router and a gateway? And I usually tell them, well, one letter. Because really, that's about it. It's a term that you can use interchangeably. A gateway is just a device that bridges two separate networks. Some people will say two disparate networks, meaning different networks. They could be two different subnets and IP. They could be two different protocols. They could be two completely different network infrastructures. And when I say voice gateway, that's primarily what I'm talking about. It's a device that can connect you from, let's say, a voice over IP network down here over to maybe a network like the PSTN. So it can grab an incoming call from the PSTN to your company, and maybe your general number is 555-1000. So it receives an incoming call to that number, converts it, and then sends it out as voice over IP. Likewise, it can take a voice over IP call and convert it out to PSTN format. It truly is fulfilling the form of a gateway between two completely separate networks. Now, it doesn't have to be that way. You could have a voice gateway between two voice over IP networks, and there's many cases that you will. But voice gateways are just upgraded Cisco routers capable of communicating with new types of networks in new formats. Hop over here to the H323 Gatekeeper, and you have a Cisco router, once again, that now has the Gatekeeper version of the iOS, which usually means a couple $1,000s more in licensing fees. I'm going to try and squish the Gatekeeper a little bit into this slide and then explain it a lot more later on in this video. But the Gatekeeper, I always call it the Lord of the WAN. You may have seen the Lord of the Rings series where you have, Frodo, and the Lord of the Rings is kind of this dark force behind it. Well, in this case, you have this H323 Gatekeeper, insert Darth Vader sound here. And this is watching over the entire wide area network. And it has two major roles. Essentially, you can picture a network that looks like this. We have this gatekeeper who's sitting in the middle of maybe two major companies. Over here on the left, I have Nabisco, who makes Fig Newtons. Over here on the right, I have Keebler Elves. And they are fierce competitors, but sometimes need to talk. So we have a WAN link going between these two, and you have this H323 gatekeeper that's sitting in between them. Now what this acts is as the Lord of the WAN, it's the independent authority to, number one, manage WAN bandwidth. I'll just put WAN BW. It watches that WAN bandwidth, because if the bandwidth ever gets exceeded on that line, all the calls just start sounding shoddy. Packets are dropped, the conversation crumbles, it's just horrible. So it watches the WAN bandwidth to make sure it doesn't exceed. And if it does, it can quickly redirect or divert a call off to a PSTN cloud that's a secondary link between those two companies. Now, the second thing it acts as is, as I always say, it's the white pages. The official term is E.164 number resolution, which means it can resolve phone numbers. So when Keebler calls a phone number over here at Nabisco, it doesn't have to have the whole numbering plan for Nabisco. And likewise, Nabisco doesn't have to have Keebler's whole numbering plan. They rely on this independent gatekeeper up here that manages like the white pages of the network, the yellow pages. You're going to thumb through it, say, "Excuse me, gatekeeper, do you know how to get to this destination?" Gatekeeper says, "Why, yes, I do. This is where you go." Now, the big thing I want to make sure you catch on this slide, and we'll get more into this later, is nobody's going through the gatekeeper. The gatekeeper is just an authority. These routers have WAN links between each other. Let me just put little router symbols on them. They can communicate directly. If a phone over here calls a phone over here, it doesn't have to go up through that router and to the other side. Once it knows where that location is, it gets redirected across the most efficient path to get it there. So this is just kind of a, like I said, the Lord of the WAN. It just makes sure the authority is there and then routes the call. Finally, these last two, we have an H323 MCU and various other miscellaneous application servers. The MCU stands for Multi-Point Control Unit, and what it was primarily used for, well, not too long ago, was just for conference calls, audio conference calls. You might think, well, why do you need a separate server for all that? Well, it's actually a very intense thing to do. You can think of it like this. One of the things that, depending on where you are in the world, it may be different. But here in America, one of the latest and greatest things is reality TV, where all of the shows are supposedly real time and real people and all this stuff. It's it's stupid. But anyway, they have reality TV for everything. And one of the shows I stumbled on recently was So You Want to Be a DJ. And it essentially is all these people that get together and whoever can, scratch records and all this kind of stuff as fast as they can, mixing all these different audio sources, are kind of, awarded the DJ award and win a bunch of money or something like that. But I've seen, this show and these guys get up there and they just have like 9 record players and they've got one playing a music tune and they're mixing in all these beats and all they do is like, I can't even begin to describe it. But it's essentially taking all these different sources and mixing them together. And that's just a small picture of what you can think of when you think of a multi-point control unit or any device that supports a conference call. It has to have all these different sources coming into it. Take just a three-party conference call that's happening, and they're all talking together. This MCU unit is busily taking all their audio inputs, mixing them together, kind of like that DJ, and streaming them out as a single stream. Now, I said that this used to be just for audio conferences, but nowadays, in recent years, they now have video MCUs. This is and it's a short, it's actually called Video MC, which sounds much like a DJ. What this is for is to mix together both audio and video signals and to keep them all synchronized. So essentially, you can have a video conference now that looks kind of like the Brady Bunch. You have like this tic-tac-toe thing. I think I talked about this a little bit earlier. But you have all these faces of all these people in your company, and the person talking, you see a full motion video and the audio stream from everybody else. It's, like I said, it's like the Brady Bunch. You can see all these people's heads all around the screen that are all in the conference call. And it's the job of the MCU or the video MC, depending on what marketing term you want to use, to mix all those signals together and stream them out to each device as a single data stream. Finally, you stumble into the various other application servers. And, I have this one tailing off the bottom of the screen here just because it's just getting silly with how many different application servers we have. For instance, we have things like Unity for voicemail. That runs on its own server with Exchange, Microsoft Exchange as a backend. We have things like IP-IVR for interactive voice response systems that can record digits, integrate with databases for things like dial-up banking and that sort of thing. We have IPCC, which can encompass multiple servers that runs an entire call center all on different servers. And the funny thing is even the voice field is becoming more and more specialized. And let me just take a moment while I'm talking about these various other application servers just to encourage you and discourage you all at the same time by saying you'll never learn it all. This is something that took me months of therapy to come to. I will never learn it all. I've gone through routing and switching, gotten the CCIE certification. I'm thinking, oh, I'm done. No, that's just the beginning. You get into the voice world. You get into IP phones. You learn how to set them up. Oh, I'm done. No, it's just the beginning. There's so many different platforms that even the voice over IP world is becoming a field in itself that you can specialize in. They now have technicians that are nothing but Unity technicians. Call the Unity guy, and the Unity guy comes over and works on that. You have get the IVR gal on the phone, and you call her, and she knows the IVR system. To where it's kind of one of those things where you can specialize and get your own niches. All this stuff that you have over here, IP phones, call agent, H323 gatekeeper, this is all in the foundation voice system. You can deploy that and still not have a voicemail system, which is kind of like the core of a voice network. So that's why I just want to encourage you and discourage you at the same time that don't worry about learning everything in this voice field because it's impossible. I've tried. There's new things coming out every day, and it scares me. But at the same time, I realize that nobody will ever know every single piece of this network. Although I did once meet one fellow who had all 4 CCIE certifications. Kind of freaked me out. He was a weird guy. I bet you he knows it all. But normal people don't. So finally, before we get into voice over IP and setting it up, Thoughts to ponder before you jump, before you make that jump into voice over IP. Thought number one, quality of service. You have to have quality of service deployed network wide before you can dream of voice over IP. Matter of fact, one of the worst stories I ever read about, I love reading white papers and kind of case studies just because they're interesting. And you see where people made mistakes and what they did right and all that kind of thing. And I read this study on a company called Merrill Lynch, who deployed Cisco voice over IP throughout about a quarter of their network. And they were migrating away from a PBX, and about a quarter into the migration, like I just mentioned, they put up the flags and said, stop, rip out the whole system and put the PBX back in, and they totally ditched voice over IP. They're not moving to it. Maybe sometime down the road they will, but definitely not anytime soon. And reading through this case study, one of the major reasons why they yanked it all out is because just about every other call would get dropped, would get crackly, or would just have blips in the conversation. You couldn't understand the other side because there was no proper quality of service deployment before they actually made that huge move. Without quality of service, your network's doomed to fail because you're going to be competing with all the other traffic that's out there for bandwidth, and without special markings or putting this first priority on all your voice over IP traffic, it's just going to be considered like anything else. And for a data network, it's okay to drop packets here and there because TCP will take care of retransmitting those. Not so with voice over IP. And Cisco thought it was so important that they made the quality of service course one of the core of the CCVP, the Cisco Certified Voice Professional Track. One of the first exams that most people take will be that quality of service because it lays the correct network foundation before you add anything on top of it. Once you have quality of service configured, you can then put your voice on top of it. This is the first way that you can do it in a campus IP telephony design. Now, maybe like you, maybe this is just me, but when I was first learning of campus design models way back when, the first thing that came to mind was a college campus, and that's what I thought campus design model meant. For years, I went through thinking campus meant college campuses. Well, in that sense, it's a good good misthought, I should say, to think that way because a college campus is a very similar design to a campus design, but campus applies to any major building or major location for a company. It's anything with high-speed, wide-area network connections between the different locations. So in this case, I have a campus in a single building, but this could very well represent a college campus with 10 or 100 buildings all connected through high-speed connections. In a campus IP telephony design, you can have one or two major gateways that connect you out to the PSTN and a wide-area network connection. Now, in this design, the wide area network connection will most likely only be used for your data traffic. That makes it very easy to deploy quality of service in this network because all of quality of service needs to be deployed on the LAN connections, which if you make a mistake, it's most of the time okay because LAN connections are what? 100 megabits per second, gigabit per second, even more, that you can squeeze the voice into, and there's very low packet loss. The calls are then transferred out to the PSTN. This, a lot of times, is where companies will begin, just doing a campus deployment, or maybe a single site, whether it's a small site or a large site. But inside of here, we have all our IP phones connected, in this case, to a multi-layer switch, which is connected to our group of 3 different call agents down here, our call managers, which act as the brain for this network. And then over here we have our various application servers, and these are things like our voicemail servers, maybe our call center applications if we're running a call center, or interactive voice response to handle incoming calls, or auto attendance to answer calls. I mean, all those applications, we'll talk about them later, but those are all grouped together back here in these application servers. In this example, I have 2 different gateways that are elected here, maybe running HSRP between them, and they both have connections to the PSTN and wide area network. That eliminates a single point of failure at a major part of our network. Now, these don't have to be equal links. They could be, maybe this is a T1 line to the PSTN, and this is just a few what's known as FXO ports, analog connections to the PSTN. And we'll talk, again, all about these different terms later on. But they don't have to be equal in rank. They just need to be backups for each other. It would be just as Just as easy if you had a limited budget to have a single gateway with 2 connections. It's just at that point you've pegged a single point of failure. As that single site campus grows, you'll start branching off primarily to small remote offices. Maybe you bring up a huge 100 or 1,000 person site next to you, but most people will branch off and have just smaller offices that come up. In this case, I have a remote office over here and maybe one of those few lucky people that get to work at home all the time, the famous telecommuter. Over here we have a central site, and this is just kind of mirroring our campus deployment with not as much clutter. I have my IP phones, maybe this is a 100 or 200 person building. Everybody has internal calling to that multi-layer switch. This is their voicemail, their IVR servers, all those separate applications. Over here I have the call agents, and then I have my redundant connections to the PSTN and WAN, and it could be one, it could be 2 different routers. Now your complexity starts increasing as you add sites, because you look over here, let's start off with the remote office. The remote office has that same router, maybe it's just a lower end router, that has 2 connections, one to the PSTN and one to the WAN. Now notice over here, there's plenty of stuff missing. There's no voicemail servers, there's no call agents, because in the central site deployment design model, these phones and all the remote devices rely on this central site for intelligence. Now, with that in mind, that can be a huge problem based on this wide area network connections. See, these IP phones without a call agent or a call manager in this case are paperweights. I mean, if they can't contact the call manager, if that connection goes down, these things stop working completely. So let's find our single point of failures. If we have one router here, if this router goes down, single point of failure. If the WAN link to that router goes down, single point of failure. If this WAN link goes down, single point of failure. If this router goes down, it's kind of like, If you're talking to a PBX person, they're going, no, So what you can do is you can help this out by eliminating all the single points of failures from this line all the way over to these call managers by deploying a service on this router known as let me grab my pen here, SRST. I mentioned it before. It stands for Survivable Remote Site Telephony. What it means is if this wide area network link goes down, or I should just generalize this and say if this router or these phones cannot connect to the central cluster over here for whatever reason, immediately this router takes over as their control unit. That's right, this router becomes the brain for these phones. They say, hey, the little beacon comes out, little thought bubble, bloop, 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 bloop. Help! I can't contact my central source. That thought bubble reaches this router in the form of a packet, and this router goes, I'll take care of you, little buddy. On the screen, you see a little code that says Cisco SRST engaged, and now this phone has the ability to still call out to the PSTN. So now they can make calls even to the central site. It's just now you're paying long distance instead of all the calls going across the wide area network to reach that central site. This is also huge for emergency calling. So if this link goes down and somebody dials 911, these phones can still dial an emergency number. Now I know 911 is an America thing, but there's emergency numbers all over the world. So that keeps those emergency services available for those devices. Now it gets even more complex over here for the telecommuter. Here's the problem. The telecommuter most likely will not have a dedicated WAN link unless the company just has money to spare. Most of the time, instead of this being the WAN, you end up with this being the internet. And how do we connect across the internet? You got it. A VPN, a virtual private network. So first off, we're encrypting all the voice. So into that, you have to factor a delay budget to the voice because we're adding encryption on top of it. Also, when you're going across the internet, is there really any guarantee that that voice will get there? No, not really. The internet is missing that big piece of quality of service. So we're just kind of taking a risk in a sense that we're crossing our fingers that the telecommuter makes it across. Now, with that being said, the internet has bandwidth to spare, and most of the time that will have no problem communicating across the VPN connection to the central site. People like Vonage or companies like Vonage have staked their entire company on that fact, that even though the internet has no quality of service, voice most of the time will make it across successfully. So we can afford to have some quality of service degradation down here at the telecommuter site, but most of the calls will go through just fine. The final design model is known as the distributed multi-cluster design. What this is, and notice I, I kind of got tired of drawing all these lines. Imagine all these connected together. What this is, in my opinion, is the future design of all networks everywhere. Networks across the world will all have their own managed entity. Take any size company. We'll throw somebody the size of Intel out there. And maybe over here we have Motorola. Two enormous companies that are managing their own voice structure, inside of this box. These couple phones, switch, and couple call routers or call agents are representing, hundreds of offices all around the world that are all communicating together. Now, they'll have their separate systems, they're all managed, but they'll all communicate eventually down the road. IP version 6 will be a mandatory protocol for this. We'll all be communicating across the WAN, which will eventually emerge to be the one major network of the world, the internet. And in this case, we have all these networks that are communicating together, and this is where we have the mother of all routers. It's enormous because it is the H323 gatekeeper. Remember, the Lord of the WAN? It's watching all of the bandwidth of the internet, ensuring that those calls placed will go through successfully and not have any bandwidth constraints. It's also acting as the phone book, if you will, of the internet. Now, as of right now, I have just this enormous routers representing it, but that is kind of a symbol to represent a new hierarchy that will emerge. Now, I have H323 gatekeeper up there, but most likely will eventually emerge with something known as a SIP standard. Again, I'll talk about all these protocols later, but these will be the directory sources that are configured very similar to what we know as DNS today, where we have our root DNS servers of .com and .edu, and those branch down to first level DNS servers, and you have this hierarchy that's configured. Eventually, you'll see some sort of hierarchy of gatekeepers set up to where they're managing all the connections of the internet, and they are essentially your white pages to call anybody on the internet. The PSTN will still be around for many years to come, but it will become more and more and more a backup network. That's why all these PSTN carriers are now offering high-speed internet services. They see this migration taking place. They know eventually these clouds will become one and the same, and everybody will use just the cloud, echo voice after that, to communicate across the networks. So all of this will converge, and every company will have its own clustered setup where all the intelligence is within, and once we deploy this strategy across the internet, even outside of the company. So we've taken our first glimpse into the world of tomorrow, starting off by looking at the two call control models. We saw the centralized call model, where all the intelligence resides in one place, and then we had the distributed call model, where all the intelligence resides in each device across the network. Most likely finding a hybrid of those two, where we have a centralized source with a distributed minor configuration, that's where that SRST comes in, to keep the routers running if the central connection is lost. We looked at the pieces of telephony in the same way we saw the pieces of the PBX, and defined the major components that we're going to see throughout the rest of this course on our IP telephony networks. What is the thought to ponder before you jump? Fill in that blank. Oh, come on, you remember. Quality of service. Before you ever dream of deploying IP telephony, first off, think of quality of service. That has to be in place before you can move on. And finally, we saw the three IP telephony network designs: the campus deployment, a single site. We saw multiple sites that are centrally managed, where the remote sites get all their intelligence from that central source. And then the final one, where it is a distributed cluster design, where every single site, or corporation is the way I spun it, has all of its intelligence in that location and relies on an outside source, some kind of outside entity, to do all the WAN bandwidth management and number resolution. I hope this has been informative for you, and I'd like to thank you for viewing.